Welcome back. I would like to spend a little time talking about wave shaping, and that's involving circuits and diodes. One problem that seems to present students with some difficulties is problem 1066 in the textbook, and I would like to work through that to try to talk about this idea of wave shaping. How do we assume which diodes are on or which diodes are off, and how do we analyze such a circuit? Let's begin by reminding ourselves of what we have. We have a circuit that involves a constant input voltage Vn, but we're allowing or we're looking at that particular input voltage at different possible values. It might be at -2. We want to know, okay, what's the output voltage going to look like if the input voltage is a constant -2? Or what is the output voltage going to look like if the input voltage is 3 volts, a positive 3 volts? Those are the kinds of questions that we're trying to determine when we're looking for this transformation or this transfer between the output voltage, which is labeled here at the output node V0, and the input. When we put in an input, what kind of output are we going to see? This is a 1K, here's a 1K, this is a 2K, and I might actually label those with variable names so that we can tell which variable we have. Maybe I will label this one, well, let me wait until I get to that point before I start labeling those resistors, but I may want to make sure that we know which resistor I'm playing with at what particular time, and I might do that by assigning a variable name to those particular resistors. This diode I will probably call diode 1 or D sub 1. Here's a diode D sub 2, and typically we like to know how is that diode behaving in the circuit. Is it on? Is it off? And all of that refers to the anode end of the diode and the cathode end. And I've come to learn or see that sometimes the cathode is actually referred to by a letter or variable K. We want, for this diode to conduct, we actually would need the anode end of the diode to be more positive than the cathode end, and we'll get more into that as we work through this particular problem. There's the anode end of diode 2 and the cathode end of diode 2. You're probably looking at that circuit and saying, what in the world is going on? And that's what we want to try to think about here. And one way to approach that is to realize that we have a circuit that involves diodes. Those are probably going to be on or off. We have one source, and that source is actually going to be constant. What may be confusing is that we're allowing that constant to vary between -5 and +5, but we're really wanting to check, or we are checking, what the circuit or the output voltage for a range of input voltage values. And what we should really think of is Vn is simply a constant. Maybe that's a -2, maybe it's a +4. We want to know, if it is fixed at +4, what does V out look like? We have, in addition to diodes in this one source, we have resistors in that circuit diagram. the diodes are off or on, that means they're either open circuited or they're looking like a pure wire if we're assuming ideal diodes. If we just have resistors and diodes, we have wires and resistors. And then we have an input voltage, and we're measuring an output voltage across a resistor. That's really saying that V0, the output voltage, really is probably just some scaled version. So V0 should be a scaled version of Vn. That's what we should be anticipating happening in this particular circuit. Let's make some observations about this circuit. And one is that the diodes in this circuit, as I've already mentioned, are connected to each other in a maybe a little bit strange way. The diodes are connected to each other really sort of in opposite directions, meaning both of their anode ends are connected together. It's not anode to cathode that we're seeing. Or the anodes of both diodes are connected to each other. Now, in general, for a diode to be forward biased, or for an ideal diode to look like a wire, to be forward biased, or for the diode to conduct, and now I'm speaking of a normal diode, not a Zener diode. We're just looking at typical normal diodes, and in this problem we're assuming those diodes are ideal. To be forward biased for a normal diode to allow current to flow in the forward direction. That's what we're really sort of meaning by a diode being forward biased. Then a diode's anode side, or pin, or terminal, a diode's anode side must be at a higher voltage or more positive than, maybe I should spell that out, more positive than the diode's cathode side or terminal. A picture of that is simply that if we have, here is our conventional diode, here's the cathode end, here's the anode end. We really want the anode end to be more positive than the cathode end. If we think of the anode end being at a voltage V sub A relative, let's say, to some reference value, and the cathode end V sub K relative to some reference, then for this diode to be forward biased, or for the diode to have a current flowing through it, I sub D. Remember, you can think of a diode as a one-way valve. It's either allowing current to flow or it's off. We really want, for this current to flow, we want V sub A to be bigger than V sub K. That's for the diode, excuse me. For the diode to conduct, in what's drawn as the forward direction. And we can look or verify that by simply applying KVL to this configuration. We have minus V sub A plus V sub D plus V sub K equaling 0. If we solve that for our diode voltage V sub D, that's V sub A minus V sub K, and if V sub D is positive, that's what we need for the diode to conduct, and that means that the anode voltage, or that pin, is going to be more positive, or V sub A is bigger than V sub K. So V sub D is greater than 0 for the diode to conduct, and that's what we had said we needed to have happen. If we go back to our circuit, it's a little bit maybe challenging to figure out what's going on, but in this case, because we have both anodes connected together, we're not going to have both of those diodes forward biased at the same time, which means that we will have one diode on and one diode off. The other thing that's a little bit tricky or maybe difficult to see in this particular problem is why, these grounded positions. But if those are two grounded positions, the ground or the reference node is at the same potential, let's just connect those with a wire and get rid of that ground, and then we can figure out hopefully what's going on. That's the other hurdle that we need to deal with in this particular circuit before we can really feel comfortable with doing the analysis. So the question that I'm trying to answer is, what do we do with the two ground locations, or how should they be handled? And I've actually hinted at what we are going to do. We're just going to, since they're at the same potential, let's just connect those 2 points. And we can connect them with a wire. Or let's connect the 2 ground locations in the circuit with a wire or a short circuit. And now the 2 points, it's obvious, I hope now, that the 2 points are at ground, which is the same potential. Or they possess the same potential or voltage. Let's now connect those by redrawing the circuit. That's figure P1066. We have our source. Again, that's a constant source. It's going over here. And we have our 2 diodes that are connected anode to anode. We have a resistor and another resistor combining to give us our output. And this is now our negative terminal of our source connects to those 2 points. What we want to do now is simply connect this point, the ground point, to that point, and recognize the fact that our voltage that we want is our output voltage right there, and that's across this 2K ohm resistor. Here's diode 1, diode 2, 1K, and 1K for our circuit elements. That's now a re-sketch of the circuit. We now need to analyze it, and what I have mentioned before is because the diodes are connected back or in opposite directions, because the diodes are connected to each other, in opposite directions, then they can't both be on at the same time. Then one diode will be on, and the other diode will be off. So we're looking at one diode being on and one diode being off, not both being on or off at the same time. So we really only have two possible configurations. Diode 1 could be on, diode 2 off, or just the opposite. Diode 2 could be on and diode 1 could be off. And now you're saying, well, which diode is on? And now if we remember what the problem was, we wanted to look at different values for the input voltage Vn. We wanted it to be either positive from 0 to 5 volts or negative from 0 to minus 5 volts. And that means that we're probably going to be biasing that circuit in both of these conditions. One condition when Vn is positive, we may have one diode on and the other one off, and then when we take Vn negative, we'll have just the opposite diodes on and off. But what you shouldn't get too hung up on is making the correct selection up front. So let's just remind ourselves, don't worry. Let's just pick a particular diode to be on. Just pick one diode to be on and see if the analysis or the assumptions that we have made support that choice, and if not, we'll just change what we're doing and go back and make the necessary corrections. Let's not worry then, we'll just pick a diode to be on, turn the other one off, and if we've done that, then the diode that's off, if we can verify that that diode that's off, if its voltage across it from anode to cathode is negative, then we know that we made the right assumption. If it's positive, then we know, wait a minute, this circuit, the way it's configured, is not supporting the fact that that diode would be off. It's basically saying this diode would be conducting, and we'll just have to go back and make the necessary corrections. Let's now remind ourselves that Vn is either positive or negative. And we don't know which one it's going to be. Let's just pick one, or we have to look at it in both scenarios, but we don't know when we pick it to be positive which of the diodes might be on or off, or if we pick it negative which other combination is true. Let's just pick one to start and then see if the analysis supports that decision, and I'm actually going to try to pick it so that it's the wrong selection as far as the combination of Vn being positive and one diode being off or on, and then we'll be able to see what you could do if you were confronted with that particular situation in an exam. So let's just pick one, or let's pick Vn positive. and see what happens. So now just remind ourselves, let's suppose that Vn is greater than 0. Now we're saying what's going to happen in that circuit. What happens to V out if Vn is 1, if it's 2, if it's 3? Well, we don't know yet. And we don't know which diode to say is on or off, and maybe we are getting confused by trying to do the analysis on the circuit and guess which of these diodes might be on or off. So let's just assume one combination. Let's assume that D1, diode 1, is on, and again we're assuming that Vn is positive, and if this doesn't support that conclusion, we'll just have to make the changes at that time. Suppose we assume diode 1 is on and diode 2 is off. If that's the case, let's redraw our circuit under those conditions. If diode 1 is on, then it looks like a wire. Here's our input, and again we were saying Vn is positive as far as we know. We said diode 1 was on, meaning it looks like a wire. Here's our 1K ohm resistor. Diode 2 we were assuming was off, so we're going to open it up. And remember our polarity. Here was our anode end and here was our cathode end. And if that indeed is going to be off, if that diode's going to be off, then V sub D sub 2 needs to be negative. And maybe you can see that that's maybe not going to be the case, but let's just keep going. Here is now our circuit. Here's the 1K. Here's the 1K. Here's the 2K. Here is our output that we're after. And remember, this was the negative terminal of our input, but we also are connecting the ground points, and those are those 2 points. And this may or may not look like you want to analyze it, or it may look a little bit funny in terms of analyzing it. So let's, if you can't see what's going on, just redraw the circuit, and maybe when you're redrawing it, label some things so that you don't get lost. Let's just label that point and those combinations of wires 1, so that means this point's 1. That means, let's just say this point is 2, and let's call this point 3. If we follow 1 around, here's 1 also down there, and we need to make sure that's just the same voltage, that's the same point in our circuit. And let's now redraw this circuit to help us see what's going on. And to do that now, we have our input voltage, and that now goes to node 1. Node 1 was connected to a resistor, a 1K ohm resistor. And what else do we know? We also know that the negative terminal of our supply or input was at node 3. Between node 1 and node 3 was a little bit of a mess, so we also had node 2 in there. So but between node 3 and node 2 was a resistor. Let's say here's node 2, and that was, if we go back, that was a 1K ohm resistor, And I'm going to call that R sub 3 since it's touching node 3. We also have a 1 k ohm resistor between node 1 and node 2, and I'm going to call that R sub 2. And then we also have, if we go back to our circuit, we have this is still node 1, and so node 1 is also the negative side of this 2 k ohm resistor, and the positive side is connected to node 2. Let's now draw that. We now know that the negative side of this output resistor 2K was connected to node 1, and the positive side of that was connected to node 2. And I'm going to probably call this one R sub 1. That's now our circuit that we can redraw to try to analyze what's going on. And this is Vn. Depending on how you see this, we're trying to find V out is equal to something Vn. We know that it's probably going to be a scaled version of Vn, and we're trying to now find that relationship. We now need to do some circuit analysis, but what we might do is, well, let's not worry about whether diode 1 or diode 2 is on or off, but we can go back and try to find the polarity that was associated with diode 2, and we need that to be negative for it to be off, and that polarity was then plus to minus between nodes 1 and node 3. So let's put that on our diagram. Our diagram now says that V sub D sub 2 is going between nodes 3 and 1, with node 1 being the negative side, and, I'm sorry, node 1 being the positive side, and terminal 3 that we had labeled was the negative side. We need that to be negative. Obviously, it looks like that's not going to be the case, because what do you see right now? We already see that V sub D sub 2 is the same as Vn, and so Vn is going to be, we said, positive, and so that's not going to support our previous assumption, but let's just keep going. We want to analyze this circuit, so let's now just say, how do we analyze it? So let's say that you didn't see that Vn and V sub D sub 2 were equal, and so for this circuit to be true or in play, we really need Vn to be negative. But we can do that later. Let's say that you didn't see that at this stage of the analysis. Let's just analyze the circuit. And if we go back, it really depends on how you see this circuit. But what is maybe making it a little confusing is the fact that we have that particular resistor down there between what we would like to have as our reference node right down here, and have it to be the same as that, but it's not, because of that resistor down there between those two locations. And we also don't have our output voltage oriented the way we might like, but we'll just deal with that particular situation. So how do we solve this circuit? Well, we could do some KVL equations, and then we would have, I see, two loops, excuse me, if we wanted to, or excuse me, now what I'm seeing we could also do is we could combine the R sub 2 and the R sub 1 into a parallel combination, and then just have one loop, and the voltage dropped across the parallel combination of R1 and R2 is V naught, or the negative V naught, and we could then just do our analysis that way. Maybe you didn't see that, and now if you did write KVL equations for this without doing any kind of reductions, so now we're saying, how do we solve this circuit? And I hope now at this point in the semester you're saying, well, there's all sorts of ways that we can solve it. Some might be more straightforward than others, and it just depends on how you see the particular circuit at the particular time. If we did a KVL, then that would say we have two loops. Again, if we didn't notice that parallel combination of R sub 2 and R sub 1. Well, what if we did KCL? What do we have? Then we have, if we look at this, if we viewed node 2 as our reference node, then we would have a voltage across R sub 3, and we would have voltage, or V sub 3, and we would have V sub 1. Let's just, maybe this won't be very convincing as far as how you would solve this, but let's just say, okay, here's V sub 3, and we're calling this now our reference node. And if that's our reference node, then let's call this V1 relative to that reference node. And now we have two node voltages, and we would like to solve those. And if we were doing that, we would be saying, okay, what's the KCL at that point? And we would look over and see, wait a minute, we have a source over here, Vn, and we don't know what the current's going to be flowing from, let's say, right to left, from V1 to Vn. It will just be the current that source needs to supply. Well, that source is now between two of our node voltages, and that should then remind you of the fact that, oh, maybe we could then enclose that in a super node and just worry about the KCL equation relative to that light blue highlighted node that we've now introduced. So let's call that A, and let's try to write now a KCL at the supernode A. If we go back, the KCL here, we had two node voltages. So that's seeming to indicate it may not matter if we don't simplify the circuit, whether we do KVL or KCL, and you guys would probably want to do KVL because KVL is more comfortable for you. That's fine, but let's just see if we can do this with KCL, and that involves then these two node voltages, V sub 1 and V sub 3. If we now do the KCL at node 3, we can, if we identify some currents flowing, let's say, out of that light blue highlighted supernode, we have I sub 3, we have, let me say I called that I sub 2, and let's call this one I sub 1. Those are the only three currents that we have flowing. There's no current here since it's opened up. It's an open circuit. We have the sum of those three currents at this supernode. We have I3, and they're all out. I2 plus I1, that's equal to 0. Did I label those particular resistors by, yes, R3 I've labeled, that's the horizontal resistor. R1 is the far right vertical. R sub 2 is the far left vertical resistor. Now I can find I1, I2, and I3 in terms of my node voltages, V1 and V2. And remember, I can do my relationship between my node voltages by using what I know to be true relative to the supernode. And I can write a KVL equation with the supernode. I can find minus V3 minus Vn plus V1 is equal to 0. And I'll use that then to relate V1 and V3, or eliminate or get rid of one of those. But for now, let me just say that I have for I3, that's V3 over R3. I sub 2 was V1 over R2, and I1 is V1 over R1, and that's equal to 0. If we look inside or at the supernode, our KVL relative to that said that we had minus V sub 3 minus Vn plus V1 is equal to 0. We can use that information to say that V1 is now equal to V3 plus Vn. We'll use that here, and now we'll just have V3 in terms of Vn. So we now have V3 plus Vn and V3 plus Vn. We can use that relationship or that information to now give us what we need. We can use that information to give that KCL equation the information we need. This is R3 plus V3 over R2 plus V3 over R1, and that's equal to minus Vn over R2 minus Vn over R1. And we can now replace these values. This was 1K, this was 1K, this was 2K, this was 1K, and this was 2K. Let's clean that up, those denominators. Let's get rid of those denominators by multiplying through by the least common multiple, which is 2,000. If we multiply by 2,000, then we end up with the following. We have 2 plus 1 V3 is equal to minus 2 plus 1 Vn. Or we now see that V3 is equal to minus 2/5 Vn. And from our observation near the output, if we're looking at the output equation of this, if we look at KVL near the output side of this circuit that we've just redrawn, hopefully you can go back and see that minus V1 minus V0 is equal to 0. Or we can see that V0, or the output voltage, is minus V1. We can also look at the KVL near the input, And this we saw, I think, by inspection before. We had minus Vn plus V sub d sub 2 is equal to 0. And that says that V sub d sub 2 is equal to Vn. And we assumed Vn was positive. And if that's the case, then we know that V sub d sub 2 is actually should be on in this circuit. So V sub d sub 2 is not off when V sub n is positive. Or another way of continuing is to just say, well then if that's the case, then we're actually in the condition or the situation when Vn needs to be negative to do the analysis of the circuit that we presently have. So let's just switch the sign and say thus, let's let Vn be negative for now in this circuit configuration. So now let's let Vn be negative. To complete this part of the problem. And we also now know that near the output we have V out is equal to minus V1, and V1, if we remember, at the output side, we have V out plus V1 is equal to 0 of our circuit, if I can find where that circuit is. If we went around here with a KVL, we see that we have V naught plus V1 is equal to 0. And so now we have V naught is equal to minus V1. But V1, if we remember what it was before, V1 was just Vn plus V3. And now we can hopefully get V out in terms of Vn. V out is equal to minus Vn plus V3. Vn is a given input, but V3 was minus 3/5 Vn from our earlier analysis. Or we now have minus 1 minus 3/5 Vn, or that's minus 2/5 Vn is what V out is. Meaning, now that we've changed the sign of Vn to be negative, now we know that if Vn is negative, then our output of this circuit, this wave shaping circuit, is minus 2/5 times that Vn. But now Vn is negative, and we're taking the negative of a negative, and so V out will be positive. And if we just pick a few of these, suppose that Vn is minus 1 volt, then from this relationship we see that V out is minus 2/5 times that 1, minus 1, or V out is 2/5, a positive 2/5. If Vn is at the furthest extreme for its negative value of minus 5, V out is now minus 2/5 times that minus 5, or it's now equal to 2 volts. And if we wanted to sketch that, here is V in, here's V out. We just found that when V in was -1, V out was 2/5, and when V in was -5, V out was 2. And we should be able to now connect that. It's a linear relationship. It's just a scaling of -2/5. That's now what V out looks like when V in is negative. Let's now look at the other half of this, or when now in that previous analysis we had D1 on and D2 off. Let's now look at the other case where D1 is off, and let's let D2 be on. And we also know now that our input must be what it wasn't before, and for this biasing relationship with D1 off and D2 on, then we know that Vn should be positive. For this diode behavior. Let's now sketch this new circuit. We have a completely different circuit because of the different combination of on diodes and off diodes. We have Vn still. Now we go over, and now we said diode 1 is off, diode 2 is on. We have our two 1K ohm resistors, and we have our 2K ohm output resistor. Our input voltage negative terminal is connected to that particular point, and these ground locations are connected. Here is now what we were calling R2 before. Here's R3, and here's R1, our output. This was 1K, 1K, and 2K. Our anode side of diode 1 was there. And if we need to, again, let's label these points, because maybe now again we want to re-sketch this to make this circuit look a little bit more familiar to how we like to sketch or analyze a circuit. So we have terminals 1 and 3 across our input voltage Vn. Here's 1 and here's 3. 3 is also connected with R sub 3, and R sub 3 is connected to terminal 2, or node 2. This is R sub 3. Here is 3. Here's 2. And between, need to go back, between 2 and 1 is R sub 2, a resistor. And so here is terminal 1, and the diode polarity for diode 1 was between terminal 1, or node 1 I should say, and node 3, with node 3 being the positive or anode side of diode 1. And now Vn is positive. We want V sub D1 to be negative, and I hope it's clear that that's the case in this configuration. This was resistor R sub 2 connected between node 1 and node 2, and between node 2 and node 3 we also had our load resistor R sub 1, which was 2K. And this is now our output voltage, positive on node 2 and negative on node 3. We're now in a position to analyze this circuit. This circuit looks a little bit more familiar to us. We can now say, okay, let's do, or more standard maybe, let's say KCL at node 2. We have this current, we have that current, and we have that current flowing out of node 2. We then have, and this node 2 voltage is actually at V0 in potential, so we have V0 minus Vn over R2 plus V0 over R3 plus V0 over R1 equaling 0. That's KCL at that output, or at node 2. If we plug in, or if we factor out common variables V0 and pull or push Vn to the other side, we have that scenario. Again, if we multiply through by 2k on both sides, we have 2 plus 2 plus 1. V out is equal to, and R sub 2 was 1, so we multiply by 2k and we get 2. V in, we now say, or can say, that V out is 2/5 V in, and as just a check, we could say, is diode 1 actually off, or is diode 1's voltage negative? If we look at the KVL that we've already sort of looked at, we have minus Vn minus Vd1 is equal to 0, or Vd1 is minus Vn, and Vn we're now assuming was positive. Then that says that Vd1 is negative, and that's what we wanted. So now we know that when V in is positive, V out is 2/5 of V in, and we can go through the same kind of logic that we had before. If V in is 1 volt, then that says that V out is going to be 2/5 of that 1 volt, or 2/5 of a volt. If V in is at the top end of that positive side, V out is now 2/5 of 5, or 2 volts. And we now know that in terms of input-output relationship, if this is V in, 1 and 5, and this is V out. Now on the positive side, when V in is 1, we know it's 2/5. When V in is 5, we know it's 2. And again, it's this linear relationship. If we combined what we had when V in was negative with this particular analysis when V in was positive, we now have the answer that maybe you already knew between this transfer relationship between V in and V out, where if we put in anything between 0 and minus 5, we get something out between 0 and 2. If we put in a positive V in between 0 and 5, we get a positive V out between 0 and 2. And that's the answer to this particular problem.